Welcome back, Honors Chem students, to Module 2 in the acid-base unit. In this short lecture, I'm going to be talking about how we determine whether something is an acid or a base, and to do that, we usually use what are called indicators, acid-base indicators. We find those in solid form, liquid form, and then we also are going to talk about what happens when you take an acid and a base and intentionally mix them together. Since they're opposites, they do what you would expect them to do. They would cancel out, and they would undergo what's called a neutralization reaction. Okay, so let's get into it. First thing, indicators. For hundreds of years, if not longer, humans have been using natural indicators to determine whether a substance is an acid or a base. What these natural indicators are is they are substances that will turn one color in an acid and a different color in a base, or they'll just change color in an acid but not in a base. So they're things that change color when they're in the presence of the hydronium or the hydroxide ion. And that's actually really useful. In middle school, you might have remembered using litmus paper um, to test whether something's an acid or a base. That's the most common ones you would find in like a high school chemistry lab. But you have three options here in this list that are all different types of paper, and what those are is they're paper that are laced with the pigment of, in this case, the litmus plant, but pigments found in plant stalks and flowers. And those pigments naturally will turn certain colors in different pHs. And so, just to review a little bit, for red and blue litmus paper, if you had a base, so in a base, if you were to take red litmus paper, red turns blue. Okay. The blue litmus paper stays blue. So blue litmus paper is really not that useful. It's not telling you, if you dip something in blue litmus paper and it stays blue, it's not telling you that it's a base. It could be water, it could be something that's neutral. But this right here, that is the key. So blue litmus paper is not really useful with bases. Red litmus paper is really useful to identify a base. Okay, so it turns blue and a base, right? If you have, if it's in an acid, okay, so if you're in an acid now, the blue paper turns red, and that's really useful. The red stays red, which is not very useful. So just like before, okay, just like before, one of them is not super useful. The one that is useful here is obviously the one that changes color, that. Okay, so red and blue litmus paper, although useful, are not overall the best type of paper, litmus paper we could use. The better type is what's called pH paper, and I just want to show you really quickly. pH paper. This is the kind of pH paper that we would use in class. There are different types of it, but it's basically a yellowish paper that is laced with different pigments that will turn various colors in different pHs. So you can see that it'll turn reddish and orange, red, orange, and yellow colors in acidic, and it'll turn usually dark green into blue purple colors in bases, and then a light green if it's in a neutral solution. And you can see here are litmus papers or pH papers that have been dipped into various substances, and you can see that the same paper will turn multiple colors of the spectrum based on how strong the acid or how strong the base is. Okay, so if we were in class, we'd be using those, but that's obviously much more useful because it can tell you whether a substance is an acid or base or neutral, and also how strong or weak that substance is. Okay, so that's pH paper. Universal indicator is pretty much pH paper. It's pH paper in liquid form. Okay, so you could drop liquids into it, and the liquid would actually change color. Phenolphthalein is an indicator that I will talk to you more about when we do Module 3, which we do titrations in. That becomes very useful during that, but that's an indicator that turns pink in bases, pink or purple in bases, and it's clear in acids. But I'll go into that a little more later. Okay, and then you see phenol reds listed here. The only reason that's listed there is because we used that in the very first week of school. If you remember back, we did that reaction in the plastic bag where the white powders turned to yellow. Phenol red was used in that reaction, so you're familiar with that. Natural pigments, flowers planted in certain soils will come up different colors because of the pH value of the soil. So this slide, you can certainly zoom in and look, but it's showing you tons of different types of indicators and at what pH level they change color, right? This one might be easier to see. Phenolphthalein, for example, the one that I mentioned we'll be using during titrations, you can see here it turns from clear over to pink or purple at about pH 8 is where it changes. But these are all very useful. If I wanted to have something that changed at a pH of 3, right, I might select one of these. If I wanted something that changed at a pH of 7, right, I might select one of these. So you can look at that on your own time. But those are indicators, okay, and they're just that. They're designed to indicate whether you have an acid or a base. Okay, very basic information there. No pun intended. Next, neutralization reactions. Just like what they sound like, it's where one thing neutralizes something else. Okay. So when you react acids with bases, they neutralize each other. So this is an acid, this is a base. Now before we talked about acids donate H, bases accept H. When you put an acid directly with a base, a full acid and a full base together, and they neutralize each other, if you look, right, there's a negative, there's a cation, or sorry, there's an anion, there's a negative ion, the chloride ion, and there's a positive metal, positive ion, a cation in the base. Those two will come together to form an ionic compound, right? Now you know that NaCl is salt. It's table salt. But in chemistry, we actually have a term. When we say salt in chemistry, we don't always mean table salt. Salt is a very broad term that refers to hundreds or thousands of different types of ionic compounds. Okay. And then you also get water. So this is actually important. Neutralization reactions will always produce, right? The products of a neutralization reaction will be water and a salt. Now understand that a salt is not going to be NaCl all the time. Salt doesn't have to be table salt. Okay, so salt refers to an ionic compound that does not contain these guys. Okay, so I'm going to put a little line through those. It can't have those ions in it. So typically it's going to be a metal. It's going to be a metal, right? A positive ion that's bonded to a negative ion of some sort, and that negative ion cannot be one of those. If it's anything else, we're gonna call it a salt. So there's an example here in the notes, and you probably should pause the video here and try to answer this question. So I'll give you just a few seconds here, but maybe pause the video, try to answer, circle the ones that are salts. Okay. So first of all, looking through this, it says it has to be ionic, right? So that's covalent, so that's not going to work. That's not a salt. Okay. Ionic, the rest of these, the other 5, they're all ionic. So now we dig down a little further. Do any of them contain hydrogen as the anion? Well, this guy had hydrogen in it, but we're not talking about that anymore. So none of them have that. Hydroxide, do any of them have hydroxide? Yes, that has hydroxide in it. Do any of them have just straight up oxygen ions? Yep. Okay. which means this is an ionic compound that doesn't contain those ions. That one is, and those three would be considered salts. Okay. So when you do these reactions, you're going to get something that resembles one of these guys with water. And salts, for the most salts are going to be neutral or close to neutral in solution, which means this reaction has neutralized itself. So let's just go through three examples fairly quickly. These are examples that you might want to follow with the first one, and you might want to pause the video and then see if you can do the other ones on your own. But they're basically double replacement reactions that we learned earlier in the year. And let's just go through them. So sodium hydroxide, I trust at this point that you guys are all in a position where you can use your periodic tables, find the charges for these ions, and write your equations out. Okay, so if you follow the structure, right, sodium plus 1, hydroxide minus 1 is going to react with nitric acid. Now you don't know what that is, so we give you the actual formula, even though we did talk about it earlier in the notes. So that's nitric acid, HNO3. Now, neutralization reactions are full out reactions. They don't go backwards, they're not reversible. So you just draw a solid arrow. And then you think to yourself, if I'm going to get a salt here, what's my metal going to be? My metal is going to be sodium. What's my nonmetal or my negative ion going to be? It's going to be the polyatomic ion nitrate. So we are going to get NaNO3, that's my salt. And then if you look at what's left over is you have OH and you have H, right? Which, if you were to write it out, would be written like that, but that's kind of a silly way to write that, so we can combine it into what we know to be H2O. Okay? And the very last thing we need to do is we need to make sure that this is balanced. And it is. It is. Okay, so that would be good. So if these two were to react with each other, they would react in a 1-to-1 ratio. And so in Module 3, we'll start looking at what's called a titration, which is where we purposely react an acid with a base, and we do some stoichiometry with it. Well, this would be easy stoichiometry because it's a 1-to-1 ratio. But we're getting ahead of ourselves. Let's move on. At this point, I would suggest that maybe you pause the video and try to do these two, and then go back and check against the video when you play it again. Okay, but I'm going to go through lithium hydroxide. Lithium is +1, hydroxide is -1, so that's what that's going to look like. Sulfuric acid is H2SO4, it's given to you. All right, if these guys were to react, you are going to again have your metal and your nonmetal, which is a polyatomic ion, and that's going to form lithium sulfate. If you look at the charges though, they don't cancel. Lithium's +1, sulfate's -2. So with that in mind, we have to make the formula fit. Okay, so we always write our formulas correctly. And then if you look here, right, we're going to have OH and H. Well, that's going to make water. Now, you might say to yourself right now, the atoms don't add up, right? H2O, and then there's an H left over. Don't worry about the numbers balancing out when you write the formula. The definition says that water is produced. We can figure out the missing atoms by balancing the reaction, which is what we're going to do now. The last thing we do is we balance the reaction. If you look, there are 2 lithiums on the right. So I'm going to make myself 2 lithiums on the left. I have 1 sulfate, I have 1 sulfate. If we count up the hydrogens, I've got 2 plus 2, that's 4 hydrogens. So I can put a 2 here. That gives me my 4 hydrogens. Now if I count up my free oxygens, not the oxygens knocked up in sulfate, right? But those free oxygens, I've got 2 and I've got 2. So I am balanced. Now if you were to do a titration, or if you were to do stoichiometry with this reaction, they would react in a 2-to-1 ratio, and the stoichiometry would be a little more complex. Okay. Last example, phosphoric acid, H3PO4, reacts with barium hydroxide. Barium +2, hydroxide -1, so that's going to be Ba. Remember parentheses when you have a polyatomic ion. Those are going to react, and then it's always a good idea to identify what your metal is going to be. Well, hydrogen is not going to be the metal, the barium is going to be the metal, and the phosphate is going to be your negative ion. So you're going to get barium with phosphate, right? Look at the charges now. Barium is +2, phosphate's -3, so that is not going to work as written. So we need to cancel our charges out. However you do that, either you do it mathematically or you crisscross the charges down. It's up to you. And then we're going to get water. Okay. And it's obvious that this is not balanced, so then we have to go through the process of balancing. I have 3 bariums on the right. I'll give myself 3 bariums on the left. I've got 2 phosphates on the right, so let's give myself 2 phosphates on the left. Okay, in terms of oxygens that are not tied up in the polyatomic ion, I've got 2 times 3. I've got 6 oxygens, right? So I'm going to need to put a 6 there to give myself 6 free oxygens. And if with any luck, I should have 12 hydrogens on the left side. I've got 6, and then 3 times 2, I've got 6, so that's 12. So it's balanced out. If you were to do a calculation with this, it'd be an even more complex ratio. It'd be a 2 to 3 ratio. Okay. So if you look, these are really no different than what we did in previous unit when we did our types of reactions. They're just double replacement reactions. That's all they are. Okay. So in review, right, we learned that neutralization reactions, we can write them out and balance them. They're going to produce water and some sort of an ionic compound called a salt. And then we talked about indicators and how they change colors at various pHs and how that's useful for us to identify whether a substance is an acid or a base. Okay. And that is, yeah, the end of this module. It's a very short module, so it's kind of a nice little relaxing few days. But obviously, look at the notes, right? Do the homework and finish up the homework quiz at the end of the unit. Okay, we will see you again in Module 3. Take care.